This is problem 511. In this problem, you have the base plate of an iron, which has a thickness of 7 millimeters and is made from aluminum alloy. You're heating it up with an electric resistance heater on one side, but on the other side, you have radiation and convective heat loss. So, what the problem is asking is to estimate the time required for the plate to reach a temperature of 135 degrees C. It does give the hint that numerical integration is suggested in order to solve the problem, but we're going to be using a finite difference approach instead. And the reason why the red box is drawn around the 511 up in the upper left-hand corner of the problem statement is because of the requirement for computational resources. So, in this problem, we're going to take this base plate and we're going to assume that you don't have any edge effect. So, if you don't have any edge effects, then effectively what you have is an infinite slab with a thickness L. We'll say a very large slab where the top and bottom have a known surface area A sub s. Therefore, the volume then is going to be L times A sub s. Underside of this slab, you're going to have QH double prime, and on the top, you're going to have then convective heat transfer. You have an H and T infinity. There's an emissivity associated with the top, and you have radiation out to surroundings at T surroundings. You're also provided with the material properties rho, C, and K. So given all this, which we'll list out here in a minute, we want to find the time for the iron to reach 135 degrees C. So we're given a few things here. L is 7 millimeters, or 0.007 meters. A sub s is 0.04 square meters. H is 10 watts per square meter Kelvin. K is 180 watts per meter Kelvin. Rho is 2,800 kilograms per cubic meter. C is 900 joules per kilogram Kelvin. Emissivity is 0.8. And T infinity and T surroundings are both equal to 25 degrees C. So, in order to solve this, we need to come up with a few assumptions. And the first assumption that we already mentioned is that we're going to ignore the edge effects. Which effectively turns it into a one-dimensional problem just through the base plate, as opposed to around the edges of the base plate having some 2D effect there. But we're even going to simplify it further. We're going to say that the lump capacitance approach is valid, although we're going to have to prove it later on. So, with these two things in mind, we're going to solve the problem. And the third thing we're going to assume is that the properties of the material are independent of temperature. So we'll say constant properties. So, with this in mind, we'll go back to our diagram here, and we'll first draw a control volume around our plate. We know we have the heat coming in from the heater, and coming out we have convection plus radiation. So we can then apply our first law. E sub dt is equal to E dot in minus E dot out plus E dot gen. This is a transient problem, so we have to keep that dE sub dt term. We know that E in is QH. We know that E out is convection plus radiation. And we know there's no generation. The energy inside the control volume is going to be the mass times the heat capacity times temperature, since we're going to assume that all the energy within this control volume is thermal energy. And we know that QH is going to be the heat flux applied over the entire surface area. Convection, we know, is H times AS times T minus T infinity. What we're going to assume using lump capacitance is that the temperature at the surface is the same as the temperature everywhere else inside the base plate. And Q radiation using Stiff von Boltzmann is A sub s epsilon sigma times t to the fourth minus t surroundings to the fourth. So let's go ahead and simplify this all out here. So we have d over dt mct qh double prime as minus h sub as t minus t infinity minus a epsilon sigma t to the fourth minus t surroundings to the fourth. And the next step is to plug in for mass rho times volume and examine the fact that volume is a sub s times L, and the mass times the heat capacity can be put outside of the derivative since they're constant. So this yields rho a sub s L C d temperature d time is the heater flux minus h times a sub s t minus t infinity minus a epsilon sigma to the fourth minus t surroundings to the fourth. So let's divide through then by everything here on the left side. So let's divide through by that. So that goes away. Get rho ASLC for the denominator of all three of these terms over here. A sub s's will cancel out. So what we're left with then is the temperature d time by itself on the left. We have QH double prime over rho LC minus H times T minus T infinity over rho LC minus epsilon sigma T to the fourth minus T surroundings to the fourth over rho LC. So what we want to use then is a finite difference approach. What this does then is we're going to take the temperature d time, convert that to t at time step p plus 1 minus t at time step p over delta t. We're going to use an explicit formulation, so we're going to take the temperatures at time step p in both the convective and radiative terms here. As a reminder, if we're going to do an implicit approach, we would take it at time step p plus 1. So now we can simplify this out as t to the p plus 1 is equal to t to the p plus q double prime h delta t over rho LC minus h delta t over rho LC to the p minus t infinity minus epsilon sigma delta t over rho LC times t to the p to the fourth power minus t surroundings to the fourth. So this alone is enough to allow us to do the finite difference approach. However, what we could do is do something a little bit more clever that allows us to consolidate terms in a way that makes it easy to evaluate the bump capacitance approach as well as the explicit time step criterion. As you can see, the problem here is the radiative term because that's the only nonlinear term in the whole problem. So we can use an old trick. We can convert the radiative term to what is essentially a heat transfer coefficient for radiation. So the Stefan-Boltzmann law, as you know, is A epsilon sigma t to the fourth minus t surroundings to the fourth. If we use the difference of squares formulation, it becomes A epsilon sigma t squared plus t surroundings squared times t squared minus t surroundings squared, which we do with another expansion, t squared plus t surroundings squared times t plus t surroundings times t minus t surroundings. Then what we get then is effectively everything within the little box here is like a radiative heat transfer coefficient. But it's a function of temperature, so it's going to vary at each temperature. So we can plug that in then to the above finite difference formulation. So what I'll do is I'll grab this formulation here. can copy that, and then I'll paste it down here. Do a little tweaking here. So we're effectively going to replace then epsilon sigma times the temperature to the fourth terms with h rad at T, and we'll make it T to the P power, so since we're using the explicit formulation, times T to the P minus T surroundings. Furthermore, T surroundings we know is T infinity. So essentially, this allows you to combine this term with the convective term. And we'll use an effective heat transfer coefficient, which is a function of T sub P, because that's going to equal H plus H rad T sub P. So what this does then is allows us to simplify the above expression as follows: T to the P plus 1, T to the P, plus Q double prime H delta T over rho LC, minus H effective T at time step P times delta T over rho LC times T at time step P minus T infinity. So one last thing we'll do is first we'll rewrite this term here as capital Q sub H. And if you look at the units for this, it turns out the units are Kelvin, which is what we expect. And then we can examine this term right here. We'll simplify that. This H effective delta T over rho LC, we multiply the top and bottom by L over K, we get H effective L over K times K delta T over rho C L squared. So this K over rho C is alpha, which means that this term here is a Biot number and this term here is a Fourier number. So therefore these things combined is just Biot times Fourier. So we can write it out in its final form then. And so we can put our equation now in its final form. T at time step P plus 1 is equal to Q sub H plus 1 minus Biot times Fourier T at time step P plus Biot times Fourier times T infinity. But since we have it in this format, we can also evaluate the criteria for Biot and Fourier, which we're going to evaluate at each step. At each step, the Biot number must be less than 0.1 for lump capacitance to be valid. Also, 1 minus Biot times Fourier has to be bigger than 0 for the stability criterion. So we'll check these two things out when we do the Excel spreadsheet. So this is our Excel spreadsheet. We can see that all the parameters that are given are provided here. What we'll do is we'll go ahead and name everything. So that'll be L, rho. You can't do C because that's reserved for columns, so we'll say C sub P. Which, by the way, since this is a solid, C sub P is the same as C. K, UPS for epsilon, H, T infinity, T surroundings, which is the same as T infinity, it's really not necessary. Initial temperature, final temperature, we'll say QH, KS, and sigma. One of the things that's important that is seen here is the initial temperature. What this problem entails is you're taking an iron, it's starting off completely cold, and you're adding in the heat through the heater, and some of that heat you're adding in is lost out to the surroundings by convection radiation. So this implies then that the initial temperature is the same as the surrounding fluid and surroundings temperature, which is 25 degrees C, which is 298 K. So we're going to use that here in this problem. Notice also that all the temperatures are written out in terms of Kelvin because you need to have everything expressed in terms of Kelvin because of the radiation term. So in order to calculate the effective radiated heat transfer coefficient, you need to have everything in terms of Kelvin. We have some other parameters we have to define here. We need to come up with a time step value. We can start with 5 seconds, and we'll see how well that works. We can calculate then what our capital Q sub h is using this dt, which we'll make sure we label that. So capital Q sub h is equal to little qh times dt over rho times L times Ct. And again, the units for that are Kelvin. We can also calculate what the Fourier number is. The Fourier number is going to be k times delta t over rho times c sub p times L squared. The Fourier number is dimensionless. So let's call this capital Q, since we already have a Q sub h, let's call that capital Q. We'll call that Fourier. Okay, so at each time step, we're going to calculate the time as the step times dt. And so at each time step, we can calculate our effective heat transfer coefficient in watts per square meter Kelvin, which then allows us to calculate out our BO number and 1 minus BO times Fourier, which then allows us to get our temperature. And at time step 0, we don't need to know what the effective heat transfer coefficient, BO, and Fourier are. All we need to really know is that at time step 0, the temperature is the initial temperature. So that's easy enough. And we'll say this is in Kelvin. So at time step 1, we click and drag this down. We now are solving our energy balance. So the effective heat transfer coefficient is equal to H plus epsilon times sigma times our temperature at the previous time step squared plus the surroundings squared times temperature plus T surroundings. So that gets us a value then of the effective heat transfer coefficient, and then we calculate our BO number is equal to our effective heat transfer coefficient times L divided by K. Which you can see is a very small number, which is good. If it's below 0.1, it means the lock capacitance is indeed valid. And then 1 minus the BO number times Fourier is greater than 0, so that's good. And then we can calculate T sub P is equal to capital Q plus 1 minus BO times Fourier times the temperature at the previous time step plus BO times Fourier times T infinity. So you can see it's jumped up after 5 seconds from 298 Kelvin to 301 Kelvin. Now we can simply drag this down. You can see now the temperature is going to grow. We want to reach a final temperature of 408 Kelvin. So see how long that takes. It looks like it's somewhere between 165 and 170 seconds. So a preliminary answer here is that the time required is about 168 seconds. Now if you notice here, the BO number always stays below 0.1 for all times, which is a good thing. That means lock capacitance is valid. And 1 minus BO times Fourier is always well above 0, which means that our explicit approach is fine. Our time step value is sufficiently small enough. So what we can do is to check this, we can use a different time step value, say a delta t of 2 seconds, and see if we get a consistent result. So if we drag these cells down, you can see that time required for it to reach about 408 is indeed about 168 seconds. So this answer appears to be correct.